All right, Rob, I think we should begin. So first off, welcome everyone to the second lecture in the Data Science Distinguished Lecture Series. I'm very fortunate we are all very fortunate to have Professor Aarti Singh here, who is an associate professor in the machine learning department from Carnegie Mellon, and I'll say a few more words about her shortly. So, this is our second in the series for the Data Science Institute. We're really excited to be able to roll this out this quarter as part of the launch of the Data Science Institute. It is a new unit at the university, and really it has a very ambitious charge, which is to set the vision of data science as a new discipline, from the UChicago school. We're going to do lots of research in order to do this field definition work. This includes really feeding and seeding the right research at the interdisciplinary boundaries of data science, as well as the deep foundational problems that exist. We're fostering and forming partnerships with our local Southside community, industry, government, national, and even international organizations to ensure that as we develop data science here at the University of Chicago, it's informed by the data science that is happening everywhere across the globe. We have gotten a good start on our approach to data science education with the launch of the new major this fall, and it's been very exciting to watch the students engage with that. And we're really taking a holistic point of view to the data science education. I'd like to just acknowledge the people that are leading the Institute right now, and that is, and what I think is very exciting about the Institute, it is chaired by it has a co-directorship of the chairs of both the computer science and Michael Franklin, as well as the chair of statistics and Dan Nicolai, who are leading the Institute and have really been working on data science at the University of Chicago for maybe almost 5 years now. I'm the executive director, if I didn't say that before, I'm Dave Duminsky. And joining us as well is Nick Feemster, who's the faculty director of research at the Institute, as well as Rebecca Willett, who's the faculty director of AI. Just as a preview of some of the work we're getting started here at the Institute, again, I mentioned some of the research activities. We are, launching very big research initiatives here at the Institute to really work on the field definition and foundational problems in data science. We're working very hard partnering with industry. We've set up the first couple of industrial affiliates that are engaging with UChicago through data science. Really excited to be rolling that out publicly shortly. The centerpiece around education and partnership across all three areas is really what we're calling the Data Science Clinic, which is an opportunity for students to engage in teams to work on very hard, bold data science problems in partners outside the university as well as inside. I'm very excited to also mention that we're having our second Rising Stars in Data Science next month. We had a tremendous number of applications to join our second Rising Stars program in data science, and I'm really excited to welcome them on campus next month. The education programs have already begun. I'm also the academic director of the MS in Computational Analysis and Public Policy. Our undergraduate major, as I mentioned before, is rolling out. The minor has actually been in existence for a couple years now. And we're just really excited about the opportunity to do as much innovation in the education space as we know we will do in the research area. Well, without further ado, today we're having Professor Aarti Singh join us. Just as a mention, next up is Professor Jenna Waynes from the University of Michigan, and we're really excited to see her talk there. And rounding out our speaker series is Gary Clifford, who's the chair of biomedical informatics at Emory. And again, so Aarti is joining us as an associate professor from Carnegie Mellon. Her PhD is in electrical and computer engineering from the University of Wisconsin. She has numerous awards, which I'm very excited to mention. Just a couple of them are really ambitious, like the Nico Haberman Faculty Chair Award. She's chaired many of the important conferences that we all sort of attend at ICML, AI Stats. And we're really just excited to have her join us for this second speaker series. So maybe, Aarti, I can have you take it away from here.
Sure. Thanks, David. Thank you all for the invitation. This is really an honor. I'm excited and thank you for listening. So I'll start by first making sure you can all see my slides. I believe they're good now. Okay. So yeah, I'll tell you a little bit about a line of research that I've been looking at in the past few years. So maybe just giving some background. So I started by looking at closed loop AI systems, essentially feedback-driven mechanisms where the machine learning algorithm is not just presented with a large data set and is making predictions, inferences using it, but is actually thinking about what data should be collected, right? So this also refers to decision-making on what should be the actions taken by, if this is an agent that's using the machine learning or AI algorithm, or even in terms of like making improving the learning, where should new data be collected? So I've been doing a bunch of work in this direction, but more recently, I've gotten interested in thinking about what other ways we can really leverage the human in this loop, right? Instead of just thinking of it as a purely automated loop, how can we think about humans and how they can contribute? So maybe I'll start by first giving, the story about a decade ago when everybody was really excited about big data, right? We were hearing about big data in all the prominent venues, right? And really, it has made a significant change over the last decade. We have had, performance of AI-driven algorithms that has surpassed human performance in applications such as computer vision, in text or audio analysis, right? But it has mostly achieved the success on very large, well-curated data sets, which are not just large, but actually are accompanied with what we call tags for all the input data, right? So it's not just images that you're looking at in a computer vision problem, but if the goal is detecting an object in an image, every image comes tagged with an object, right? It's a cat, dog, maybe some person of interest, and so on. There are other applications where it's text as the input, right? But every text document or piece of article that you're reading comes annotated with something about the semantics that you may be interested in learning, and so on. So one key bottleneck that we have realized in the last decade is that it's not just large data, but we really need that data to be tagged, right? To be able to then do predictions, given a new data point, be able to predict something about its semantics, about the object detection, or any of the other applications of interest. And there has been a lot of work that has also gone towards thinking about how can we remove this bottleneck, right? Or at least mitigate it. Because tagging of the data requires effort. Either it requires a human to be involved in the loop, who's then, whether it's done by an expert or in a crowdsourced way, telling you what the tag for a particular image is, or in some cases, it might require a measurement device, right, where it's collecting or observing or recording say, properties of something that you're trying to synthesize under different conditions, right? So tagging is an expensive process. And people have come up with a lot of different ways. In fact, these are the list I have here is only partial. This is basically the kind of things that I've looked at. So semi-supervised learning, the first one tries to think about how can we use unlabeled data in addition to labeled data, right? So tag data is called labels. So because we have small labels, can we also use unlabeled data to guide and minimize how many labels we might need? Experimental design and active learning, the next two things listed here, are also variations where you don't just use unlabeled data, but actually are selective about which unlabeled data provides you the most informative labels or tags that you might want to collect. And moreover, this is done in a closed loop, using the data points you have seen so far to decide what should be the next piece of data. Right? Transfer learning is another aspect where we try to have labels in one easy to obtain setting and then try to see if we can extend it to other settings that we may be more limited in terms of how we can collect the labels. But what I talk about today is yet another take on this problem, which is thinking about this human aspect, the human who's providing it, and thinking about alternate ways humans can provide supervision, not just indicating objects and images, right, or semantics or so on, but an alternate or indirect form of labels. So specifically, the thing I'll focus on is called preferential supervision. Basically, what this means is that instead of just saying, you like something or don't like something, or if there's an object present in the image or not, you provide preference feedback, right? And humans are good at providing preferences. I like this, I don't like that, right? Sort of thing. Or I like this more than I like that, right? So this is what we refer to as preference feedback more broadly, right? In a classification setup, you might be thinking about like whether to recommend a movie to to a particular user or not. And instead of having the person decide whether they like a movie or not, it's easier for them to say, I prefer this over that, right? It's much easier to give this kind of a judgment. Similarly, other problems, regression problems, where the goal is not just to categorize, but to be able to predict something, some real number of interests. For example, given images of people's faces, you might be interested in identifying what's their age. Now, guessing the exact age is much more challenging than trying to decide like who looks older between a pair, right? So this is another example where there's a preference or comparison feedback where you can say one thing is more preferred to another. And you may have seen this maybe much more routinely if you go to an optometrist to get your eyes checked, right? Then you're never asked, is this, setting of your lenses or eye prescription like, the best fit for you? They usually show you different possibilities and ask you to compare, is this better or is this better, right? So I think many of us have gone through that process. This is, again, it's an optimization or a fitting problem. They're trying to get the best possible fit for your, eye level. And the goal here is to be able to find that fit using as few possibilities as they might want to show you. Once again, rating how good a lens prescription is much harder than actually doing comparisons, which one looks more clearer or better. Yet another setting is reinforcement learning. So this is the setting where the machine learning or AI, agent is using an algorithm, and whatever actions he's taking based off of that algorithm actually change the environment, right? So I'll talk a little bit more in detail about this, but just to give an example, the way the agents work here are by a reward functions that's specified to them. It's a hard-coded mathematical metric, right, that indicates how well did the agent do. Every time they take an action, given the state of the environment and the action, they get a reward. But it's becoming very hard to specify such rewards because a lot of the problems you are deploying these agents in are highly complex. There are usually multiple objectives at play. Moreover, it's hard to mathematically capture that notion. And also, sometimes the rewards are actually delayed. So for all these reasons, there has been a lot of press about reward hacking, how people came up with reward metrics, but there were easier or wrong approaches to achieving maximum reward. So given the difficulty of coming up with this reward metric, once again, you can look at agents' behavior over time and give a judgment about which agent behavior is desirable and which one is not. And that's a feedback that incorporates a lot of these or overcomes a lot of the issues that we have with specifying a mathematical reward. Right. So, for example, a cleaning robot can achieve its objective in two ways, right? If you give the metric as the reward metric as you should not see any dirt, then clearly there's a wrong way by putting something like a bucket on its head or actually spewing back dirt versus actually cleaning it, right? But if you see the agent in action, you can give an easier judgment about which one is a more desirable approach to follow. So I hope that motivates looking at preferences or comparison feedback as an alternate form of supervision that we can try to get. Often it's easier to obtain or more accurate or less noisy, right? Or the time required to come up with the comparison. So different applications pose different ways in which preferences can be beneficial. But we'll try to come up with some more foundational understanding of, when the preferences can actually help. So just to give you a roadmap, we'll look at how can preference feedback help? And I've divided the problem domains we have looked at here in two categories. The first one is where we care about the labeling function. So classification, regression problems, threshold bandits is another one I'll mention, where we are interested in, amongst a finite number of choices, which ones exceed a threshold, right? So that's another one where we care about whatever that target function might be, and what its value is, or is it above a threshold, something like that. The second set of problems are what are called optimization-based problems. So here you may not necessarily be interested in the value of the labeling function, but actually what setting maximizes or minimizes it. And examples of this problem that we have looked at are, one is just optimization, convex or non-convex. And another is reinforcement learning, where policy optimization, finding the best policy that an agent should follow, is also relevant. So I may not have time to go over all of this, but I wanted to send a takeaway message before going into the details of any of that, which is that in these problems, and the reason I broke them into two groups is because the first set of problems is where comparison or preference feedback can help reduce how many labels you want to achieve. And the reason preferences help is because if I have comparisons or preferences, I can form a ranking of my objects, right? And once we have a ranking, we essentially have embedded our problem into a one-dimensional space, right? So now everything that we care about classifying or doing regression on, or right, deciding whether it's above a threshold, now lies in a one-dimensional ranking space. And all we need to do is now requiring few labels to then infer what the labeling function should be in this reduced space. So that's the high-level takeaway for the first piece, that comparisons can reduce the label complexity significantly to a single dimension, ideally, if the comparison noise is no worse than the labels. Now, of course, the methods I'll talk about are agnostic in the sense that they can have higher comparison noise than the label noise, but in that case, they'll just reduce to a label-based setting. The second set of problems I talk about here, and here people actually had looked at the convex optimization piece earlier and how to optimize a convex function using such comparisons. And in this case, they show that comparisons can actually completely replace labels. So you don't need to have labels. Comparisons, which is basically the sign of the gradient, right, whether the function is larger or smaller at the 2 points you're comparing, is actually enough to do the optimization. And we show that this holds true not just for convex problems, but also non-convex optimization problems, such as Gaussian process optimization, and also reinforcement learning, where we are interested in policy optimization. So in these setups, comparisons alone suffice and can completely replace the labels. So this just says, what is foundationally possible, given that you have access to this indirect form of labels, just comparisons between the labeling function values, as opposed to just knowing which one is larger than which, as opposed to knowing the value of the function itself. So I hope this piece, right, most people can take away. I will try to go a little bit more detail into some of these problems now. Okay, but feel free to ask any questions in chat if you have any. Okay, so I'll try to focus a little bit on the classification and regression setups, and then maybe reinforcement learning as an example in the optimization setting. Before I do that, let me mention formally, right, what we exactly mean and what we are looking to develop here is that we have two types of queries. So a standard machine learning algorithm just works with labels, right, in the supervised way, where you have an input X, and the label corresponds to is a draw essentially from a labeling function fyx, right? And now we are considering the setting where we have access to labels, but labels are harder to acquire. So we also consider access to another oracle, which can provide us comparisons, meaning that now the algorithm picks a pair x and x prime. And what it gets back is the sign of the difference in the labeling functions, basically just saying whether the labeling function at x is larger than the labeling function at x prime or not. And the algorithm automatically will decide which type of data to collect, how much of it to collect, and when to switch from one modality to another. And the goal is to be able to minimize the number of labels using this preference feedback in the form of comparisons while we want to achieve error epsilon. So two things are important here. One is the label complexity, which is how many labels are needed to achieve accuracy epsilon if you're only using labels, and how many comparisons are needed, right, to achieve the same error epsilon. And this may require some labels or not, depending on the two groups of problems I talked about. Okay, so I'll be mentioning results in the form of how many labels do we need to get error epsilon, or how many comparisons do we need. So starting with the first setup, which is classification using both preferences and labels, one of the problems we looked at was actually in additive manufacturing, where aerospace applications in particular, it's important that the parts that need to be printed, right, are very lightweight. And additive manufacturing has really opened up the possibilities in terms of making things lightweight because you don't have to print them solid, right? You can have hollows and voids within these materials that can reduce the weight while hopefully still preserving the strength. That's where a lot of the design comes from. But even just to decide which pieces are good candidates for additively manufacturing, this is where we were working with the Navy, and they have 40K additively manufactured compatible parts that can potentially be printed, but they needed to prioritize which ones to print. So experts in this case, right, which were people actually working on these machines, were able to give judgments about which part is more printable than another, because actually doing the print requires much careful planning and optimization of how exactly it will be printed, right? Because there are many design possibilities here in terms of you start printing the part up, which part first to which part next, and so on. So we were looking at, can we query these experts and be able to do this in a more informed way using comparisons? So first I'll talk about foundationally, right, how much this helps and what's a method that can integrate comparisons and labels. So imagine this is just a toy depiction here that you have two properties that you might care about, and you want to be able to predict whether it's printable or not. So the way the method can work is you start by deciding an uncertainty region. Initially, you're completely uncertain of the label everywhere. So this would be the whole domain. And you sample some points in that region. Now, instead of directly collecting the labels as a standard supervised machine learning algorithm would do, you start by first doing comparisons. And you don't need, even if you have endpoints, you don't need to necessarily collect all n square possible pairwise comparisons between them. You can do some active choices here. And it turns out that you only need, I think that's going to come up next. You basically only need n log n comparisons to be able to infer essentially a ranking of these objects. So what they are going to be ranked here is according to the printability of the part, right? So because we are trying to classify these parts into, right, whether they're printable or not. So it goes from the least printable to the most printable. And assuming for now, let's say the comparisons have no noise, right? We can exactly get this ranking using a bunch of pairwise comparisons. As I said, it needs actually n log n comparisons to be able to get this embedding right. And now the problem actually is very easy because you have an ordering and all you need to do is to decide a threshold, right, on this labeling. So we don't know the value of any of these labeling functions. We just know an order. But if we can draw some labeled examples, we'll be able to say exactly where to put that threshold, and everything on one side can be labeled as printable, the other side not. So we collect some smaller number of active labels. And by active meaning, again, we don't randomly just choose which of these points to get labels for. We can actually do it in a binary search way because now we know that our problem has just reduced to identifying a single threshold. So it can be done by binary search. And in this case, the error goes down as 2 to the minus little n, if little n is the number of labels we are collecting, which is much fewer than the total number of objects we started by ranking out. So we can do that and identify a threshold, and then essentially infer the labels of all the remaining pieces. What this essentially gives us is by using much fewer labels, as many labels as we just need to learn a single threshold in one dimension, we have been able to essentially label our entire, the data set we started out with, the big N points that we sampled. So we just take them back to our original space. We now have a fully labeled set that was obtained by only labeling some selective pieces, not all of them. And we can update our whatever classifier we are using in this bigger space. We can update where our decision boundary should be based on this enlarged data set. And we can shrink the uncertainty region also because we are more sure now where the boundary is, and keep repeating this process essentially. Yep. So that's just the idea that we are going to use comparisons to essentially generate a larger label data set while only collecting few labels. So I'm presenting the analysis here of this approach using adversarial label noise and adversarial comparison noise. We do have similar results for other noise settings where you can expect that your so adversarial basically means that you just take a handful of these, some small fraction, right, eta of the labels, and they are corrupted, right? Similarly, comparisons, a handful of the comparisons are arbitrarily corrupted. You could also have a setting where it becomes harder and harder to do the comparisons as you get closer to the threshold. So that's the other type of noise, but the overall takeaway is still the same. So I'm presenting results for this setting. One change is when we are doing this in the noisy setting, we change the binary search to be group binary search. So essentially, we can define groups based off of the fraction of comparisons versus labels we have, and based off that, conduct a binary search. So what we see here is that if we were in the label-only setting, which is the first row in this table, then our label complexity depends on the dimension of your input space. Theta is your complexity of your classifier, and then epsilon is the target accuracy, log 1 over epsilon. Whereas if you do this with labels plus comparison, and this is with active labels, the first piece, and if you do it with active labels and comparisons, then we only need log 1 over epsilon labels. The number of labels is independent of both the dimension and the complexity of the class, right? So that actually, the comparisons now scale like that, but you have been able to reduce the labels significantly by leveraging this. And we have corresponding lower bounds, which say that these complexities are essentially tight, as well as the noise tolerance is tight. So if you have, this essentially corresponds to the reason this is epsilon square is because if you have epsilon fraction of the labels corrupted, that's essentially like epsilon square pairs of comparisons are corrupted. So it's of the same level, right? Now, one thing you might worry with this algorithm is that it seems like because you're alternating between comparisons and then labels, if our comparisons are actually much more noisier than the labels, we might get stuck. But turns out there's an easy fix to that, which is once we identify the threshold, instead of labeling all the points, right, by saying if they lie on one side of the threshold, we have obtained their label, we only do that if we are confident in the ranking being correct. Okay? So actually, this is the idea we so the original paper didn't have this, but this came up in a subsequent work where we were applying this to a threshold bandit problem, which is very similar to classification, except that there are a finite number of things you care about. So these are called the arms in a bandit problem, and they have certain rewards. In this case, these values mu1 through μk. And the goal is to find by using as few pulls. So the standard setting is you just pull an arm, meaning you get a draw from a distribution where this may be the mean, the reward is the mean. And in this case, the goal is to find all the arms whose average reward essentially is bigger than a threshold. So the classical work here is, again, that you choose an arm, you observe some reward that's corrupted by noise, right? And how many such pulls do you need to be able to figure out the set that's above a threshold? In the comparison also setting, so comparisons are known as duals here, just because of the analogy with bandits. What you get to see is you pick a pair of arms and you get to see whether an arm beats another arm if its expected reward is larger than the reward of the other thing. So you don't get to know the value of the reward, even a noisy value. You just get to see comparisons. Which one is larger than another one? So the same idea can be applied here, where we rank all the active arms using the fraction of wins, how many times it beats another arm. And once we have done this embedding, then we just do binary search, right? But to find essentially the arm that's closest to the threshold tau that we desire. So this is very similar to classification. And binary classification, we would be comparing to half. Where does the probability of one label exceed half, or is it below half? The only thing, that's in this case, to make it foolproof, which can also be applied in the classification setting, is that we now deactivate, or the equivalent of like you label the rest of the arms, but we don't label everything. We only label the ones for which we are confident. And this ensures that even though if your comparisons are not good, you're not going to be confident in the ranking and you will not label those arms. So you just might reduce to a standard, you label in the extreme 1 point in one iteration, but you're back to the labeled only setting. So yeah, whichever things you label, you essentially deactivate those arms, and now you work with the other subset, and you keep shrinking essentially this threshold of when you are confident enough by some amount. And doing that, you can show essentially similar improvements in identifying the arms which are above a threshold. So here's how the result looks like. With pulse only, the complexity depends on how far, what's the gap between the reward of each arm and this threshold we care about. And it's summed over all possible arms. So it's inversely proportional to the gap squared. When we have pulse and duals, then we can show that the number of pulse now is essentially logarithmic in the number of arms or the number of objects you're trying to identify, whether they're above a threshold or not. And of course, that depends. This improvement depends on whether there is a comparison gap or not. So this delta IC that shows up, which determines the dual complexity, has to do with exactly whether the arms can be ranked or not. And so if they cannot be ranked, this thing goes back. So the comparisons are noisy. This goes back to being K, but otherwise you get a significant improvement up to log K, depending as long as your comparisons are not too noisy. Okay, so I'll skip the results here, but this was just showing that the red is the algorithm in both plots, which we have this rank then search, or ranking and search. I think rank then search is used for something else, but it does better than both in terms of pull complexity and complexity than competing algorithms for a passage reading difficulty classification task here. So I'll quickly mention the regression setting, which is actually very similar, where, again, the goal is that we want to be able to infer this labeling function, but without asking the direct labels of too many things. So just based off of comparisons, can we do this? And there are two applications here we looked at. One was, what's the age of a person? Trying to guess that given their images, face images. And that would be equivalent to getting the direct label, but just having them do a comparison on who looks older is an alternate form of feedback, which is the preference-based feedback. Another one is looking at Airbnb listings and trying to get people to estimate the price of some commodity, in this case, just the Airbnb listing, or asking them to say which one is more expensive. So once again, saying which one is more expensive is an easier task than actually estimating the exact value of the commodity. So a very similar idea applies here as well, where we can use comparisons to come up with an embedding right into a one-dimensional space. Now, there is nothing to focus here. There's no decision boundary necessarily. We just want to get denoise labels for all the points. So once we sample our points and we have a ranking of them now based off of their regression values, right, going for the smallest regression value to the largest regression value. Now what we realize is that one, it's again a one-dimensional problem. And secondary, we also know, just like we knew earlier that there's a single threshold, here we know that our function is supposed to be monotonic, right? It's supposed to now increase from one side to the other. So we can actually use this fact to do isotonic regression in one dimension. Isotonic regression is just doing standard regression, essentially denoising of the labels, but while ensuring the constraint that your predictions are increasing. So once again, we need some n log n comparisons to be able to sort the endpoints, and we can run one-dimensional isotonic regression, which has an error rate given here based off of how many labels we obtain, but this is much less because it's independent, again, of the dimension, the original ambient dimension. So yeah, we get some of the labels. The initial labels may be noisy, but the isotonic regression already denoises them. And essentially, we can use these to now infer, right, what the labeling should be for other points in that hierarchy, right? That's what the isotonic regression piece would do. And thinking of this, again, we've used fewer labels, and being able to infer the labels in this one dimension means now we can take all these labels back to the higher dimensional space and apply our favorite regression method there. So for example, you could go do k-nearest neighbors or a kernel regression methods in the higher dimensions, and that works fine, right? So we have essentially, again, been able to infer the label of a much larger set using a smaller number of direct labels. Right, so we could do a prediction in the higher dimensional space this way. So here again, the results look similar, that if we are in the label-only setting, then if our function is Lipschitz smooth, that's the easiest setup to consider, but we can, this extends to Holder smooth more generally. Then we can have the standard rate, which is depending on how many labels are queried, which is little n. We have a particular error rate that depends exponentially on the dimension d. But when we are using both labels and comparisons, then we see that the number of labels needed now is much fewer. In fact, this piece is again independent of the dimension, right? The number of labels needed. But the number of comparisons, of course, also shows up here. And their complexity does increase exponentially with these. So, of course, there's no free lunch here. This is just saying that if you have comparisons that are easier to obtain or cheaper, right, you can use those in lieu of the labels, except that you still need some number of labels, which corresponds to one dimension setting. So here also the bounds are almost tight up to log factors, except for the comparison complexity. We have this extra m to the minus half term, but that can probably be improved with a better analysis. But just to show you some application of this, so the first piece here, we did apply it to that face imaging task. So for this, we used a data set called APAREAL, which is about 4,000 images. And that's what you see here on the x-axis. And it contains two types of labels. So actually data sets which actually have comparisons in them are of this size are limited. So what we did was there were biological ages as well as apparent or perceived ages, which is the actual feedback you would get if you asked a person, right, available. So we used one of them as the direct labels and obtained comparisons using the other apparent ages. And we can see that if we use this ranking information, so in this case, because we had all possible comparisons, they were obtained from this apparent age. So we were able to get this embedding directly and then perform k-nearest neighbor regression in that using that expanded data set. So we see the black curve, which is much lower error than with other methods we tried, which were directly working with the labels only. So comparisons helped improve the accuracy here. And similarly, in that Airbnb price problem, here we actually went ahead and collected the data and the labels ourselves. So there were about 450 or so listings that we looked at and split into training and test pieces. And what we observed was that the comparisons, right, again, how useful comparisons are really depends on the application. In this case, we were able to clearly say that the comparisons were 10% less noisy than direct labels, meaning that if we took the comparisons and we took the direct labels and got comparisons using the direct labels, those were much more noisy compared to the direct comparisons. And we see once again that with about 900 comparisons, we were able to get much better results than just using the labels only in this case. All right, so I'll pause before transitioning maybe to the next piece. If there are any quick questions on that, we can take the longer questions maybe later. Okay, so then maybe I can say a little bit about the optimization piece quickly. So I think I had motivated this earlier, right? So for example, optimizing the fitting of lenses to your eyes, or another problem we looked at was getting expert judgments when trying to optimize material property, because experiments are expensive, but experts also bring some information that can be used. And here, once again, mentioning that other people had looked at the convex case, where they show that if you have comparisons, which is essentially like the sign of the gradient, then that suffices to give you the same rate as you would with zeroth order method. So the rate corresponds to a zeroth order method that only has function evaluations, but you can do the optimization purely based off of the sign of the gradient. And non-convex optimization is something we looked at. And even though it seems different, because here comparisons can be global, they don't have to be locally confined to even the same basin in an optimization or local minima in an optimization problem, we see that comparisons alone also suffice in this case. And the rate you get is basically the same rate as you would get with function evaluations in a Gaussian process optimization setting. So I won't go into this, but just mentioning one piece that here what was relevant was that even if the comparisons are mismatched, meaning they are not sign of the true labeling function. And this can happen when you especially have two different sources from which comparisons are coming versus where you're getting your labels from, right? If it's people giving both of them, right, both the direct labels and the indirect comparisons, then you believe that they have some labeling function in their head, right? They might be trying to get comparisons out of those. But in a setting where your comparisons are coming from an expert, but maybe the actual experiments are what give you the direct label, they could be mismatched. So even in that setting, we came up with adaptive algorithms that can identify what that level of mismatch is and only opportunistically try to leverage the comparisons while reducing to a label-only setting if there was a big mismatch. Okay, so similar to the optimization setting, I think I'll go a little bit more into the reinforcement learning setting, where I think the case for preferences is much more stronger in the sense that this is really a setup where rewards are very hard to design in complex problems. As I said, like there are numerous examples of applications where agents have performed unexpected or unsafe behavior because the rewards were poorly specified. As an example, there was a gaming application where the final reward was actually winning the race, but because that reward is sparse and not easily accessible, there were intermediate rewards that were defined based on maybe collecting coins or whatever, and agents that actually just kept hitting a lot of coins without actually finishing the race got a overall much higher reward. But clearly it defeats the purpose, right? Because it doesn't get you to the desired behavior. And preferences actually have emerged as a much more useful way of specifying whether an agent is behaving appropriately or not by looking at two trajectories it might be taking and saying which one is preferable. However, much less was actually known here that can preferences in this setup, where what you're observing is a preference between the trajectories taken by the agents, do they lose any information relative to actually having a reward at every step with every action getting a reward, right? So there was only one piece of work which analyzed asymptotic convergence in this case of a particular method, which is based off of Thompson sampling essentially. And but there were no finite sample results which allow you to compare the number of labels with the number of comparisons of trajectories that are needed. So I will talk about our analysis, which actually provides this, right? It actually shows that the number of comparisons between trajectories is comparable to the number of reward episodes that you might obtain. And they are exactly the same order, and you can still find the best policy that an agent should follow using only comparisons of the trajectories. But just to show that even though this other method was asymptotically optimal in terms of practical performance, because again, our method is more finite sample, it was able to achieve a much larger reward relative to all the existing baselines. So it's not just that there's a theoretical improvement, there is a practical advantage also to using these methods. So the formal setup is, and let me be cognizant of time, I'll try to keep this short, but that there are a bunch of finite states S, certain finite number of actions A, and a horizon. Horizon is the extent to which it's the time horizon over which the agent actually interacts and collects these rewards. And the goal is to be able to optimize the policy over that time horizon. And there's a reward which maps every state and action pair to a real number. We assume the reward is bounded between 0 and 1. There's a state transition matrix, which tells what the next state of the system will be given the current state in action. There's a non-stationary policy, which maps every state to every action. And we are interested in identifying learning the best policy, which is basically the set of actions that should be taken at every time step from 1 to edge. What we care about is the value, right? Again, not exactly the value, but the policy that gets the maximum value, where the value of a policy is the total reward it accumulates over a certain number of time steps, right? And we also assume that the total value is bounded between 0 and 1. So the goal is to find a policy that with high probability is as good as the best one in terms of this value function up to an error of epsilon. So the first interesting point here was in a reinforcement learning problem, there are lots of comparisons you can obtain. You can obtain comparisons about which action is best in a given state, right? Or it could be a comparison between, right, the reward at a particular time and state. But what we focused on, which is more natural, is the comparison between trajectories, right? Again, observing the agent behavior over time and then trying to say which of the two behaviors, trajectories, is preferable. And we assume that you can also compare partial trajectories. You can look at a piece of, right, not the entire behavior, but some part of it and still be able to make a reliable judgment. The first piece here that even with perfect preferences, noiseless preferences, one may not recover the optimal policy because trajectories may not be reflective of the optimal policy performance, right? Trajectories are random draws from the policy, and they may not reflect exactly what the policy is implying. So as a quick example, let's say we have a policy pi that has a reward 1 with probability 0.4 and 0 with probability 0.6, okay? And there's another policy that always has a reward of 0.1. So then a randomly drawn trajectory from pi prime will beat a randomly drawn trajectory from pi with probability 0.6, right? It will have a higher reward. But if you look at the expected reward of a policy, then pi is supposed to have higher expected reward. So this is just an example that says that actually, because in this case, right, it's not like the previous examples, what you're observing the preferences over and the policy is not a one-to-one mapping, right? Every policy can lead to many trajectories. And therefore, what we can end up with is intransitivities that come up because some policy is preferable to another one, that pi 2 is preferable to pi 3, but then pi 3 is preferable to pi 1. So to overcome that, what we need to essentially imply is exactly what I just sort of just said, that a trajectory needs to be, or a comparison of a trajectory needs to be reflective of the value of the policy. And only in that case, we can expect comparisons to do as well, right? So here we are assuming that if you have two random trajectories, then the probability one beats another one is reflective of the difference in their values, right? Which is a very natural assumption to have. Okay, so under this setup, we can first talk about having access to a simulator. A simulator means it can put you in any state in this, at any time step. You can be in any state, and we can start the process from there. First, we'll talk about this, but then I'll talk about what happens if you did not have, you could not start in any state, but you had to start at some initial state and then propagate. So in this case, we can actually do dynamic programming, where we are going to use the preferences between trajectories to find the best action in any state, right? And this can be done using essentially a dueling bandit routine that we discussed earlier. So we start at the very last step, right? Because we have the freedom in this case to start anywhere. And we run a dueling bandit algorithm, which tells us what the reward should be, or gives a comparison between the rewards. And we can identify the best action to take at that time step, right? That's our pi hat of h. And then we can do dynamic programming, go back one step and figure out what's the best action to take at step h minus 1, given that we have fixed the best actions at time step h, and so on, right? And this can give us the entire policy. And it turns out that you can look at, right, how much is the number of comparisons we need here and how many simulator steps are needed, right? So if every dueling bandit algorithm we are running at every state is given equal budget of accuracy and confidence, then we need this many comparisons. And we can compare this to what happens if we only had rewards instead of comparisons of the trajectories. And it turns out that this is exactly the same number of steps and the same number of episodes we would need in a reward-based RL. Now, this point is important because one trajectory is essentially carrying information corresponding to an entire episode, right? The whole time step h amount of information. So it won't be fair to compare the number of comparisons to individual rewards, it makes sense to talk about how many reward episodes we would need to see. So it turns out that there's exactly a one-to-one correspondence between these comparisons and the rewards. And as a dueling bandit subroutine, we can use any routine we in particular use as auto maximize that has a requirement which aligns with the one I said, where the trajectory comparisons are reflective of the values. Okay, so I think I would not like to spend too much time, but just to say that it is possible to replicate this when we don't have a simulator. We have to start at step 1. We can't start at step H and directly get our reward by first having a synthetic reward. So I'll just give the high-level idea without going into details, but we can have a synthetic reward that is 1 if you reach a state and 0 if you don't reach the state. So first we work with this synthetic reward. Once you hit a state, right, at step H, then you start doing the dueling bandits, right? So it's the same process as before, except we are guaranteeing you're reaching some certain reachable states that have a high enough probability of reaching by putting a reward there. And once you hit that reward, right, then you are in that state at step H, and then you do a dueling bandit algorithm here to figure out what's the best action to take at this state. And then you fix it and you can backtrack as before. If you reach it, you generate a trajectory, use dueling bandits to decide best action, and then go backward step. So we see that in this case also, the comparison complexity once again matches the number of episodes in a reward-based setting, showing that you can actually get the same number of, you can replace rewards with actually comparisons between trajectories, and it does as well. All right, so I'll just end with some open questions. I've mentioned a few that are more specific to the problem setups, like a gap in the noisy regression setting and so on. Perhaps a more important one is that there have been recent advances in reinforcement learning, which have actually shown that the reward complexity can be improved even further under slight change of assumptions to be independent of the horizon edge. Whether that carries forth for comparison-based setting is still open, because the method used there is not instance optimal, and we need instant optimal bounds to be able to say how many preferences you would need. So it's still an open question about whether just using preferences in reinforcement learning, we can also make it independent of the horizon edge, the number of comparisons, that is. But more broadly, I think there are opportunities here for thinking about adaptive algorithms, right? Right now, our algorithms are more like interleaving comparisons and direct labels, or just using comparisons. But really thinking about adaptive algorithms that can do hybrid, even in a reinforcement learning setting, which is optimization setting, thinking about some rewards that are delayed, right? May not come every round, with comparisons between trajectories that you can obtain much more frequently, maybe, right? And also, even that may have a limitation on how many comparisons you can obtain. You may be limited in the number of comparison rounds you can have. How many times you can query an expert is ultimately limited, right? Or even the crowd. So thinking about in limited interaction settings, how can these hybrid models that leverage rewards and comparisons work well? And finally, other forms of feedback, right? So people have started looking at things like discriminative features, like trying to get human feedback directly on which features make it one class versus another, right? So contrastive or discriminative features. Another is comparison of features, right? This is also another open direction where experts can provide judgments about which features are more promising, right? Or are more relevant to the prediction than another. They can give you some rough ranking of the features. And how can we take that into account when doing a prediction? Taking it one step further, we are also investigating things like experts can provide causal relations or knowledge, right, graphs. What is related to what? And how can we leverage this kind of prior knowledge feedback, which could potentially be misspecified, but can we, in a data adaptive way, use it when we don't have enough data? But as you start collecting data, right, you could start adapting to whether the information provided by the expert is actually accurate or not. So this sort of interaction between humans and data-driven algorithms, how to do it in a proper way, when to stop trusting the expert, right, and when to actually use them, especially there's a case to be made in low data versus large data scenarios. So all of these are very interesting open directions that I'm excited about. So I'll end here with just some references to the work I've talked about here, and I'm happy to take questions.
Thank you, Aarti. Thanks for a great talk. I think there's some questions coming in. Oh, great. First one is from Becca. Can you unmute or actually maybe just say or chat your question?
Hey, can you hear me now?
Yep.
Great talk, Aarti. Super interesting stuff. So one question I had is that you mentioned in the regression setting that there's this gap in the bounds when it comes to noise versus no noise. So do you see similar kinds of gaps arise in the RL setting? That wasn't entirely clear to me, like what the role of noise is there.
Right. So it's not, so I think the regression gap is something that I believe can be overcome. I don't think it's foundational, though we haven't been able to close it. But yes, there it is coming precisely because of noise, right? That there is, in the noiseless setting, yeah, there is no gap. In RL, it's not so much that there's no gap. So I think even with noise, even with noisy comparisons and noisy rewards, the parallel goes through. The open problem I was mentioning had to do with that recently people have been able to show that if you change the assumption a little bit, right, with this overall reward being bounded, if you only take that assumption, the total reward is bounded, then you can get a reward complexity that's independent of the horizon. And we don't know whether that's possible with preference-based learning. So it's under like slightly different assumption saying whether we can get independent of horizon complexity with preference learning. That's still open.
Got it. Okay, great. Thanks very much.
I already had one quick question, and then maybe I know we're running a little bit short on time. I was really excited to see the future open questions around the features themselves. If you sort of flip the script a little bit on features, when you look at the comparisons, do you actually see different behavior in terms of, accuracy, in terms of, when we think about feature ranking, right? Do the comparisons sort of feed differently into the feature importance than, a true label?
No, they do feed very differently, right? Because in one case, you have an ordering of features, like almost think of it as feature selection versus just saying I have, right, an embedding of my labeling function. So yeah, it can play out in very different ways. This is actually something I have not worked on. I was just mentioning that as an open problem that I think it would be interesting to compare. What would happen, because it's a natural setup in many scenarios. People do have especially experts we talk to. I work with some material scientists. They have a sense of consider this thing. This is the most important to optimize, and then consider this thing, right? They can clearly tell us what are the important pieces or the features exactly. So it will be interesting to look into this, but we have not. So it's an open question. Yeah.
Fantastic. So I do know we're at time. So I think what we can do now is let's give everyone have everyone give a virtual, applause here. And thank you, Aarti, for this great talk. And thanks for joining us today.
Thank you.